So today we will talk about the three-phase controlled rectifier. So before that, let's do a review of what we did for M-phase with half-wave rectifier. So here basically we had M-phase diodes connected in parallel for each phases. So if you remember those things, that thing has following the highest voltage between phases. If the voltage of the first phase is larger, then that will be in conduction. It was following that curve. Then the second one becomes the larger one among those M-phase voltage sources. And it was just following those higher ones. And actually, if you remember the half-wave diode rectifier voltage, so it was, it can be calculated from phase voltages. So it was 3 square root 6 divided by 2p times the voltage phase RMS, or it can be calculated from line-to-line voltages. So line-to-line voltage is square root 3 V phase voltage. So it is 3 square root 2 divided by 2p V line-to-line RMS voltage. So here it will be the same thing, but instead of diode voltages, we have the thyristors, the controlled rectifiers. So here you see a half bridge thyristor rectifier. So it has like 3 thyristors in a single package, and that larger ones are the power connectors, and those small connectors are for gate signals. So our equation becomes like that, and it is really similar to what we did with the diode rectifier, but instead of just jumping from phase A to phase B, then phase C, basically that transition can be delayed by applying a gate signal later on. So you can calculate that one. So I'm just leaving it to you to calculate the phase voltages and the equivalent output voltages. So the thing to remember is we have the same parts, and similar to single phase case, we have just the cosine alpha case. Okay, we have the cosine alpha case for the half bridge Thyristor rectifier. So again, it has the same disadvantages. So for each phase you only have some positive currents. So it just implements some DC offset to the grid, and we don't want that. So let's emphasize our efforts to full bridge Thyristor rectifier. So for the full bridge Thyristor rectifier, and we will do the derivations for that one. So again, we have 6 devices. So it is really similar to what we did for a single phase rectifier. So we have in a single phase rectifier, remember, we have 2 sets like that, and you are connecting your inputs L1, L2 to here, or you can model it like a single phase source. And in the 3 phase, we just add another bridge, another leg. Okay, so it becomes, once it is connected here, so it becomes a 3-phase full bridge rectifier. And now we assume to have ideal current source on the secondary side. Okay, so again, if you remembered from the diode rectifiers, those phases are conducting in pairs. So for example, at first it was coming from here, then it was coming back from phase C, or in other instances you can have, it can come from here, so then it can go back from phase B. Okay, so you can have like 3 possibilities here, 3 possibilities at the down. So there are basically 6 different switching modes for that converter. And again, if you remember, that can be represented either like symmetrical voltages for 2 half-wave rectifiers, or if you remember from the diode rectifiers, you can see the output voltages. It can be either can be represented are like difference between phase-to-phase voltages, or you can represent it as the line-to-line voltages. And if you remember again from the diode, so our output voltage is shown like here. So you have 6 different possibilities. So we have VAB voltage, VAC voltage, VBC voltage, VBA voltage, VCB voltage, VCA voltage. So you have all these 6 possibilities, and in the diode rectifier our output voltage was following the peaks of these 6 line-to-line voltages, and each of that thing takes 60 degrees, and we have the peaks of that thing, and actually we calculated the average output voltage based on that area and multiplying it by 6. This is what we did for the diode rectifiers. So it is the same, and actually if you look at the voltages and currents, the currents were, you remember, 120 phase in conduction and 60 degrees off, and 120 negative for each phase. And you can have, again I just mentioned, you can have blocks of that voltage, and this is the line to line voltage. So let's try to see what happens with a thyristor converter. So this is for diode, or you can say firing angle is 0. So when firing angle is 0, it is identical to diode rectifier. So let's see what we have for the Thyristor rectifier, right? So the first thing, the definition of alpha is equal to 0 is not measured from the sinusoid 0 voltage. So this is the first instance that a thyristor can be fired. Okay, so can be fired. Of course, you can apply a gate signal whenever you want, but it is the first instance where it is first forward biased. Okay, because if a thyristor is reverse biased, okay, even if you apply some gate signal, it will not make a difference. So it just makes a difference, okay, if it is forward biased and if you are applying a gate signal. So if you have both these conditions, then it will start conducting. Okay, so let's have a look at for that one. In order to in order for that period to be fired, to get into conduction, it should be somewhere here. If I don't know, let me show it here. If, for example, this is like one of the conduction mode paths, then you are going to jump onto that one, right? If you fire somewhere at that point, it will not make a difference, because if you just think about that circuit, right? Clean it a little bit. So let's assume at first that one is conducting, okay, at any time, okay, and let's say now that T1 is going to turn off and T3 is going to get it. Okay, so the condition for that one, if C is staying there, that voltage is, if this is our neutral, this is C voltage, so it is already seeing VAC voltage, right? So that one, T1 to T2, and VAC is the output voltage, is the peak of voltage that I'm going to get. If I want thyristor 3 to get into the conduction mode, right, that voltage B to C, this is VAC, I mean the next one, let's make it red, like that, and let's say this is VBC, right? For that point, if that T3 gets into conduction mode, then our voltage will be here VBC. So if I try to fire that thyristor somewhere here, okay, somewhere here, it will not get into the conduction because that mode is already VAC, and if that voltage is larger than VBC, like here, the thyristor itself will be like reverse biased, so even if you apply a gate signal, it will not turn on. Okay, so the instant that it can be turned on is the point where VBC gets larger than VAC, right? So if we just come back to here, let me clean that again. So that point, okay, so that point is the where you can fire your thyristor. Okay, so that is why, you know, that angle is called alpha is equal 0 degrees. So for three-phase diode rectifiers, the definition of firing angle is here, right? If I just fire at alpha is equal to 0, then it becomes, you know, like a diode rectifier. So it will be going like that, right? So now let's have a look at what will happen if this is not 0 degrees but a value larger than 0 degrees. So if I measure, let's say, that thing as 0 angle, okay, and even if diode, even if thyristor is forward biased, and if I don't apply a gate current, then this will not get into the conduction. So if it doesn't get into the conduction, but we have ideal current source, so it has to carry that current, so we will still have the same configuration for some time. Okay, it's like the single phase diode rectifier, but now it's like the single phase Thyristor rectifier, but now we are following the line to line voltages. So at that point, let's assume I just fired my thyristor. Okay, so my firing angle is that area, that is alpha. So at that instant, I now move to my next set of line to line voltages. So here we have again the same thing. The firing angle starts from here. Of course, it's technically possible to have like different firing angles for different phases, but there is no, you know, practical meaning. You will have just increase other harmonics and more ripple voltages. So it is, if you have a firing angle, it will be identical for each phase. Okay, so it will, you know, you will have another voltage here, so there will be another jump here, so there will be another jump, there will be another jump. So the output voltage is still following the line to line voltages, but instead of just keeping the maximum points, I will have delays of alpha degrees. So let me show you a couple of figures, and I hope it will be more clear. Okay, I will come back to that one. So at first I have 0 firing angle, so this is equal to diode rectifier. Okay, so whenever you have the case, then we already calculated that area, and we are using that area, then multiplying by 6, dividing by 2p, and then you get the average voltage. This is alpha is equal to 0. We will do the derivations in a moment. Okay, so if you make alpha is equal to 30 degrees, again alpha just starts from the point where you can fire, and it makes a difference. So that distance is 30 degrees. Okay, I really suggest you to draw, you know, those things, get a template of sinusoids, and draw it yourself. Okay, so it just follows that line. Let me use the red. It just follows that line, follows that line, follows that line. So you can see the building block, the symmetrical shape for output voltage is that waveform. All right, this is for 30. If I just move even further, if I just make 60 degrees, then I just start, this is my 0, and if you just go 60 degrees is the point where it just touches, but still you can delay it. So now my output voltage becomes like that kind of waveform, right? So this is my symmetrical shape. And actually, if you go even further to 90 degrees, I mean, it is not really meaningful, because now I have some positive regions and negative regions, and they are symmetrical, and V out, in this case, we will derive it as well, 0 volts. Okay, so at 90 degrees, similar to what we found in single phase rectifiers, it is 0 volts. And if you go further, now it is symmetrical to the 60 degrees, but now I'm generating a negative voltage. Okay, so again, similar to single phase and Thyristor rectifiers, this is a two-quadrant rectifier, so you can supply positive or negative voltages. And if you go to 150, it is like that, and if you go to 160, so it is identical to 0 degrees, but it is in the negative region. So of course, due to extinction angle and also commutation, that may not be possible in a practical case. But anyway, you have the same waveform of the 0 angle, but in a negative direction. So let's go back: 180, 150, 120, 90, 60, 30, and 0. So let's try to calculate that average voltage, right? So what we did is, we have that kind of waveform, and actually if you think about it, there are like two methods to calculate the average voltage. So of course, you can see that is the symmetrical block, and whatever you can have, if this is 0, this is alpha, you can calculate that angle, you can take the integral from alpha to somewhere, and you can calculate it. Technically it is possible, but if you do it yourself, you will see it's not that easy. So the easiest method, let me clean those things a little bit. So the other method is, we already know the diode rectifier case, right? It was, let me use the orange one. So previously it was following that, peaks. So there's another method that can be calculated. So I know that voltage, I already calculated for diodes. So now there's a reduction due to that area. Okay, I just lose, like in commutation, I just lose some area, and I can call that area, let's say, A alpha. So this is the area, voltage seconds area lost due to commutation, and if I subtract that area from the previous diode converter case, I can find it the average voltage. So again, technically both of methods are same, but the second method I just mentioned is easier. Okay, so let's try to have a look at that one. So I will try to calculate that area. So how can I calculate that A alpha area? Okay, so let's have more space. So I would like to get A alpha, right? A alpha, for example, let's try to find here, and that one is VAB, okay, and the other one, that one is VCB. So that area is, you know, from 0 to alpha, 0 to alpha. And what is, you know, what is the magnitude of that waveform? So I would like to get technically VAB minus VCB, right? So this is VAB, this is VCB. I want to subtract two waveform from each other, and if you look at, you know, that thing closely, VAB, VA neutral, let me write long, VA neutral minus VB neutral, which is VAB, minus VC neutral plus minus minus VB neutral, and actually they cancel each other, and what you have is VAC voltage. So that difference, you know, between two line-to-line voltages, if you subtract two line-to-line voltages, you obtain a different line-to-line voltage. So actually I can calculate the magnitude of that thing. Anyway, so if you write A alpha, right, where let's call this 0 angle, okay, 0 to alpha, 0 to alpha. And what is that voltage? That voltage is VAC voltage, right? VAC voltage d omega t, or I can write that one as 0 to alpha. I can write the peak of square root 2 VLL, or square root 3 VRMS times sine omega t times d omega t, right? So if you just take the derivative of sine, it is minus cosine. We did it many times, and let's take those constants outside, VLL times, so it is minus cosine alpha minus minus cosine 0, which is 1, so it becomes 1 minus cosine alpha, right? But this is not the average voltage. This is that area lost, okay, due to late firing angle. So in order to find the average voltage, I need to subtract the original, you know, diode voltage waveform minus that value. And actually, if you remember VD as a function of alpha, so what was the original diode rectifier case? Again, you can calculate it using the integral, or you can just check your old notes. It was 3 square root 2 VLL, okay, divided by P, right? This was, you know, the output of full bridge diode rectifier, or with alpha is equal to 0, right? So minus, I want to get that voltage drop. Again, this is not voltage, this is not volts, this is volt seconds, or voltage radians. So how many times I have that voltage? I have 1, 2, 3, 4, 5, 6. 6 times divided by 2p. So you are going to get, you know, square root t2 VLL 1 minus cosine alpha 6 times divided by 2p, right? And actually you can write that one as like that one cancels, so you have 3, okay, so 3, actually you have the same thing for diode rectifier, so 3 square root 2 VLL divided by p minus 3 square root 2 VLL, they have the same terms, in parentheses 1 minus cosine alpha. So that term and that one, you know, cancels each other, and I have minus here, another minus here, so it becomes positive. So if you have it, what square root 2 VLL divided by p times cosine alpha, right? Here. So here we started from like the original voltage as if it is a diode rectifier with firing angle. Then we subtracted that area which was A alpha, and the effect of that area to the output voltage is you have 6 times of that reduction and divided by 2p. And actually when you do the subtraction, those terms cancel each other, so you have the original term times the cosine alpha. So if you remember the equation for single phase thyristor rectifiers, we still have the same equation. So you can put alpha if alpha is equal to 0, so that becomes 1. So it is the same equation like a diode rectifier. Okay, when alpha is 90 degrees, that becomes 0. If alpha is larger than 90 degrees, then it becomes negative. So let's check that equation. 3 square root 2 VLL, sometimes some constant terms times the cosine alpha term. So here alpha is equal to 0. I have that voltage. I have alpha is 30. So we have reduction of cosine 30. So this is square root 3 of the original voltage, 0.8 something. If it is alpha is equal to 60, this is cosine alpha for this angle is 0.5. This is half of the original voltage. If you go to 90, so cosine 90 is equal to 0. So that is why it is symmetrical and it is 0 volts in net output voltage. If you go further away, then it is negative 120, 150. For 180, cosine 180 is equal to minus 1. So it is the same magnitude but in negative direction, right? So that is why we have that equation. It is identical to diode rectifier times a term with cosine alpha. Okay, cool. We have that one. So let's have a look at the current. So it is, if you look at the case here, again, I mean there are like 6 different possibilities for each phase. So each voltage has like 60 degrees of peak, but a voltage, for example here we have a conduction from one phase and then the other one changes, but the first term stays constant. So you have 120 degrees. It was the same in the diode rectifier case. 120 of positive and 60 degrees off for one phase. This is for phase A. So during that time you have the VB or phase B and C voltage, C grid lines are doing all the circulation. So phase A is off, and for 120 degrees it is negative. So it was again that typical waveform that you will see in a 3-phase diode rectifier, right? So then you can actually check those links in the presentation. We proved it for the diode rectifier. In that one you didn't have any third harmonics. Okay, in that waveform you don't have no third harmonics. So as a result you have the peak value, okay, and no third harmonic. Then you have the 5th, 7th, so you don't have 9th harmonic, and the constants are very similar to what you have with a square waveform minus the third harmonics. Okay, so we did it for the 3-phase diode rectifier. They are the same. So what is the difference? The difference is when I have alpha is equal to 0, okay, so and if I get the fundamental component of the current, okay, it is symmetrical, it is in phase with the phase voltages. So in other words, in this one, displacement power factor is 1, they are in phase. And if I just move my firing angle, and if you just take the fundamental component of that thing, you will see there is a phase difference of alpha. So we had the same relation with the single phase Thyristor rectifiers. As I increase the firing angle, there becomes a phase difference between the fundamental components of voltage and current. So for 60 degrees you have that amount of thing, and for 90 degrees, you can draw the fundamental component, and there is a 90 degrees difference. So that implies, power factor is 0, or in other words, power is equal to 0. So you have current and voltage, but it is purely reactive power. You can prove it because VDC is equal 0 also. There is no net power flow. There is of course some reactive flow, reactive power flow between load and source, but at 90 degrees you are not transmitting any power. So it is the power, the firing angle, let me write here, so firing angle controls the power factor. Okay. So, and actually I give you as an assignment to calculate, so I will not repeat it again. So if you have that kind of waveform where you have the ID, and that one is 120 degrees, and that one is 60 degrees off, and another 120 degrees minus ID. So if you take that current waveform, and if you calculate the RMS voltages for that one, then you will find the fundamental RMS is going to be like square root 6 divided by P, and it is equal to 0.78 ID. This is for the fundamental RMS. And actually if you calculate the total RMS is going to be square root 2 divided by 3 ID, and it is that value. And of course you can calculate the THD respectively. Please do it yourself as an exercise. So you calculate it as around 31% THD. So it is lower, it's lower than a pure square waveform, which was we had 48% THD. In this one I have a 31% THD. So let's discuss about the effects of the commutation. Again, I don't want to get into detailed calculations. The derivation is out of the topic of this course, but just to see what happens in a Thyristor rectifier. So it is again identical to what we have in the commutation for a diode rectifier. So the areas are same. So this is firing angle 0, and our line inductance is 0. This is the ideal case, and the output voltage is like that. And if you have, this is the case we discuss for the diode rectifier, when the firing angle is equal to 0, and if we have non-ideal grid inductance, we have, instead of if you were just fire at that point, let me use it here. So this is where you apply firing angle, so that is 0 point. But now instead of just jumping from one of the thing, it just takes some commutation time, okay, and we call it like U, and we calculated that area. So what we are having is, it's quite small, sorry for that. So we have that red areas, okay, we have that red areas lost due to commutation, right? And we already showed, I mean, this is for, let's say, 20 degrees. So we have, you know, now that area lost. We have that area lost, right? So this was, remember, AU, and we already showed that area is proportional with omega, proportional with inductance and current. So there is no term like in the area of that thing. Of course, the time, the actual time it takes is a function of alpha, but the voltage reduction due to commutation is independent of the firing angle. Okay, so this is with 40, and basically we had that figure is more clear. So we have that area lost, okay, and this is like one voltage, this is another voltage, this is the average of these two voltages. So it is same thing as in the diode rectifier case, and actually that area, I mean, I'm not going to show it again, but that area is omega ls id, and it repeats itself at every 60 degrees. So it happens 6 times in a full cycle. So what you can do is, it is, you know, if you just ignore that term, that is the identical for a diode rectifier, and you have the same thing. And this is the output voltage of a thyristor, but the voltage reduction due to commutation is identical to what we had with the diode rectifier. Okay. So I mean, just for a comparison, so for single phase we had 2 omega ls current divided by P, and for 3 phase we have just happening, you know, 3 times or 6 times in a full cycle. So, you know, if you compare the commutation voltage drop in a single phase rectifier and 3 phase rectifier, whether it is a diode rectifier or a thyristor rectifier, you will see that term always. Okay, so that term is coming to here, and this is the output voltage of a thyristor converter. If alpha is equal to 0, it becomes a diode rectifier. But as you can see here, the amount of voltage reduction is independent of firing angle. There is no term related to alpha in this equation. Okay. So let's talk about inverter mode of operation. So as you know, we discussed in the single phase thyristor rectifiers. So this is ID, and let's say this is V out, and you can have positive voltage. I mean, the current is always positive, or you can have negative voltage. When you are working at the first quadrant, okay, this is called first quadrant, this is second, this is third, this is fourth. So when you are working at the first quadrant, voltage is positive, current is positive, so you are supplying power to your load. And if you are working at the fourth quadrant, then your current is still positive, but the voltage is negative. So that implies now power is transferred from your load, which needs to be an active load like a DC machine. Then power is transferred from load side to the source side, to the grid side. Okay, so I mean, this is what you have with the commutation, and if you didn't have any commutation, that those lines will be horizontal. But here, let's say you have a really small firing angle, so this is output voltage with respect to ID. As the current increases, there is a slight reduction due to commutation, and as you increase firing angle, okay, it just comes to here. And in an ideal case, if you have 90 degrees, so it will be 0 voltage like that, and if you go below, then it goes like this. So this is, you know, the first quadrant, this is the fourth quadrant, so you can, you know, span any kind of point in that area, right? So it is possible to drive a motor with 2-quadrant operation. So how can you obtain a 4-quadrant operation? So if you remembered from machinery last year, if you have a motor, and okay, so there are like 4 quadrants that you can control this motor. Either it can be operating like you can have the voltage and current like that, like forward motoring, or you can have the current direction in the other direction, which is forward generating or braking, or instead of rotating it clockwise, you can rotate it counterclockwise, reverse motoring or reverse generating. So there are like 4 different possibilities for the terminal voltage and the current. So how can you obtain a 4-quadrant operation like that using a Thyristor rectifier? So what you can do, and this is still used in some large DC motor drives, you can connect 2 Thyristor, it can be single phase or 3 phase, 2 blocks in anti-parallel direction like that. So you can supply from here, the current can be flow like that, and the voltage can be positive or negative like that, or from the other one, the current can be flow like that. Again, the voltage can be positive or negative on the other side. So from that motor's perspective, now it is possible to operate that motor like not in just 2-quadrant operation, but in 4-quadrant operation like that. Okay, so the red area is supplied by that one, and that blue area is supplied by that converter. So using that one, it is possible to control your DC motor as much as you like, and you will see actually more detail about that thing is in your chapter 13, which is outside the scope of this course, but you will see that kind of motor drives in the next semester. Okay, so this is a a better representation, which it is controlled by 3 phases. Of course, these 3 phases are not different, both of them are connected to the same phases, and the only thing is you have 2 anti-parallel Thyristor converters in order to have current in both directions, because you cannot have current like that, but you can have current to the next set of thyristors that way. Okay, so that summarizes the 3-phase controlled rectifiers, Thyristor rectifiers. They are really similar to what we did with the single-phase Thyristor rectifiers, and also the general voltage outputs are similar of a 3-phase diode rectifier. So I advise you to take your time and plot the output voltage on your own. It will be much more efficient. Okay, thank you.